you. Good afternoon. My name is Elisabetta Carattin. I am an architect and a PhD from UAV, University of Venice. And in the next 15 minutes, I am going to introduce you to some considerations made in collaboration with Professor Vincent Brannigan from the University of Maryland. Some considerations on the limitations and the potential of the use of evacuation models in complex environments. Complex environments demonstrate the frontiers of the use of models and clearly illustrate the need to carefully distinguish between what we know and what we don't know. Evacuation models are some of the most complex programs used in fire engineering. They claim to predict human behavior and instability over the lifetime of a building in a wide variety of fire settings. They often contain hidden implicit assumptions about the evacuation environment. On the other hand, designers routinely assume conventional buildings, standard reactions, and normal wayfinding aids. This case study illustrates some of the key features that tend to be lost in the process of abstraction, especially when dealing with buildings that step out conventional design. People still die from fires, even in code-compliant buildings. They die because evacuation is too difficult, too complex, or too dangerous. Fire codes do not differentiate between simple structures and complex structures. Code makers make the heroic assumptions that complexity is not important and that code compliance is routine. For example, is there a regulation that says that emergency exit sign should be more prominent in complex structures? Consider this example. This is one of the complex environments I studied a few years ago during my PhD. Do you think that people will be able to spot that tiny emergency exit sign surrounded by all that overload information? Well, I interviewed people, and almost 80% of people interviewed weren't unable to recall the location of that emergency exit. So is that design solution still code compliant? Has all the environmental information been taken into account in advance during the prescriptive design process? Sophisticated mathematical evacuation models represent one of the hallmarks of performance-based fire safety design. While the research community and some developers may understand the limitations of the use of fire models, overwhelmingly these models are used to get a number that can be used to get regulatory approval. These models can be used by engineers with little background or training in the limits of predicting human behavior. Regulators may therefore assume an expertise on the part of the engineers that they do not have. This forensic approach to fire safety, combined with the complexity of human behavior and the very long feedback loop on building disasters, can lead to the approval of structures that have massive inherent vulnerabilities. The process of design and approval of this funnel-shaped emergency exit stair of the Comcast Center at the University of Maryland shows clearly this kind of problem. As you can see from the picture, this is a funnel-shaped exit stairs that has 5 exits on the top and only 3 at the bottom. Anyway, this design has got regulatory approval after the submission of a mathematical evacuation analysis that simply ignored the problem of crowd crush in that particular point. The evacuation modeler simply forgot that this is a sports center and that a lot of people may egress from this building. Why does this happen? This may happen because these complex issues can easily be lost when modelers forget that models are simplifications of reality. In the process of abstraction and simplification, many complex issues tend to be lost in favor of often unsupported claims of predictive power. Modelers may think that the inputs they put in models are universal and they do not take into account unknowns present in complex building. In particular, human factors represent extremely qualitative factors that are difficult to be predicted because they lack sufficient data and or a covering law. The problem of prediction of human behavior is especially difficult when applied to complex structures. namely buildings that host a lot of variables. So how would a model handle all the problems that could be present in a complex structure? Consider this example. This is the dinosaur hall at the London Museum of Natural History. This hall is visited by crowds of people from all over the world that want to admire an animated Tyrannosaurus Rex. Visitors come from all over the world, and they can admire dinosaurs through an elevated walkway that runs the full length of the room and then deposit them back into the museum's maze. As you can see, the walkway is very crowded, and there are children and also pushchairs. The walkway acts both as a viewing point and both as a holding area for crowds of people waiting to see the animated Tyrannosaurus Rex. So now let's consider the problem of predicting flow conditions in such a situation. Flow condition may be affected by cultural confusion, pushchairs that may be discarded in the evacuation process, and by the presence of smoke that can fill up to the ceiling. So are we sure that conservative default values derived from the literature are conservative enough in such a circumstance? For example, flow condition in such a circumstance could be 0. Flow conditions may be affected by numerous additional variables that may depend on the occupant characteristics on the building itself. So how do you think that a model will be able to handle all these problems? And more importantly, will all these problems be clearly stated and resolved in the engineering analysis? Evacuation modelers must be very careful when using unproven categories of variables or parameters. In the process of abstraction, the use of abstraction, that are named as if they are real can easily lead to the problem of reification, which consists of treating a variable as if it were a real entity. Walking speed can be used to demonstrate this problem. Walking speed is an abstraction, not a measurement of a defined constant. An engineer may think that walking speed is a thing that really exists, and all they have to do is go out and measure it. But the problem is that without a covering law that tells you how to project that observation, all the observer has is a single observation. And that observation can be demonstrably inadequate. As an example, observing people walking on modern, smooth, unbroken, contemporary buildings, ramps, may tell us nothing about people walking on slippery historic buildings' ramps. In addition, gradient is not the only issue on a ramp, even in non-emergency situations. In fact, gradient does not take into account human behavior and factors. Walking speed in the real world could be bounded by 0 or some large number, but the prediction of the specific walking speed in any given environment is subject to vast uncertainty, an uncertainty that almost always should include 0. For example, if you consider people in a column or a line, walking speed will be affected by the slowest component. So the greater the uncertainties, the more complex the uncertainties, the greater the uncertainty in the evacuation prediction. Evacuation modelers must also be very careful when predicting wayfinding performance of people inside of complex structures. Evacuation models routinely assume conventional building layouts and simple layouts. For example, room connected through corridors. But in the reality of complex buildings, these buildings are made up of very complicated layouts. For example, in historic buildings, evacuation paths are very long. There are few exits, Evacuation path is not obvious, and there is not virtually built fire protection. But anyway, we can see a very similar situation even in contemporary buildings. This picture has been taken inside of a long corridor of Phoenix International Airport. And even here, we have a layout made of a system of long corridors that connect large open spaces. So wayfinding difficulties may be very, very important. In addition, you can see that it is almost impossible to spot any kind of environmental information related to emergency wayfinding. And who can guess there is an area of refuge, for example, at the end of this corridor. Evacuation problems inside of these buildings can be unusually severe because in the event of the evacuation, you have to imagine a lot of people trying to figure out how to get out of this building, or get out of buildings with unfamiliar and unusual layouts. And these are the kind of people that you may find escaping through those corridors. Occupants are usually considered adult and alert, but in reality, complex buildings host a lot of children, disabled, and elderly people that may be clustered in different specific areas and that may have different situational awarenesses, like, for example, these people sleeping in an airport. We still do not have enough data on this kind of population. For example, is the exiting behavior of school children in Singapore the same as the exiting behavior of Italian high school students? And more importantly, to what level of certainty are these differences known? And do evacuation models take into account backpacks carried by students, luggages carried by tourists, pushchairs, and other items that can be discarded during the evacuation process? The more complex the building, the more likely it is to have these things in people's hands. Unlike physical sciences, behavioral sciences are very uncertain. They are observational and correlational. Explanations are situation-specific. Emergency egress models routinely have to deal with the problem of predicting human behavior far into the future without a total absence of covering laws. Fire models routinely include aleatory uncertainty, often masquerading as engineering judgment. But while engineering judgment is well interpolated, is well designed to interpolate data between known data points in the presence of an adequate physical law, it cannot be extended to extrapolating from mere observational data in the absence of a covering law. For example, the prediction of the stock market has proved to be almost impossible even when large fortunes could be made and even with a lot of mathematically tractable data. The product of human decisions can be put into the model as estimations only if they are supported by adequate data. Otherwise, uncertainties have to be treated as a condition of the model. It is therefore the quality of the input data, and the theory is therefore very important during the engineering analysis. This problem is clearly illustrated with the prediction of the changes that could happen during the lifetime of the building. Are we sure that evacuation models will predict in advance all the changes that could happen inside of a building? The values of the variables may change during the lifetime of the building. For example, here we can see the same stair with a temporary installation made of sections of timber molderings put on the stair. And years later, we can have a completely different configuration. This is another temporary exhibition, but now we have an installation made up of fixed chairs on the stairway. So we can see that in two different times, we can have a different fire load and different flow configurations. Are we sure that the evacuation modeler will be able to predict all these changes in advance? Evacuation modelers should be very careful when proposing to validate the data they put in model for the lifetime of the building. Unless there is a system designed to monitor, evaluate, and control the characteristic of the building, every variable concerning exit paths, occupant characteristics, and fire load is simply guesswork. We have seen that it is very difficult to predict building characteristics and fire load into the future, but the prediction of human behavior is even more difficult. And that can be shown by this example from the Uffizi. If the bookstore is on fire, that door is the only fire barrier to effluent spreading up the major exit stair from the collection. This is not an automatic fire door. Nothing keeps it closed in an emergency. The key safety question should be whether the guard stays at the bottom of the stairs and performs his functions properly, like the captain of the Titanic, or runs for personal safety at the first sign of trouble, like the captain of the Costa Concordia. Exactly what engineer judgment would support either assumptions. So assumptions that behavior should be reliable and predictable cannot be made without a far stronger research base. Anyway, these risks are rarely quantified and may be affected by designers and regulators' reliance on ineffective technical solutions. This can be illustrated very clearly by these two emergency exit doors. As you can see, the architect has done everything in order to make emergency exits not visible. A condition of a model may be that emergency exit sign should be visible and comprehensible. Anyway, if the condition is not met in reality, the model will not give valid results. Consider this example from another airport. As you can see, this is a complex environment, but code makers have not made any difference between a simple complex structures. As you can see, it is very difficult to understand the wayfinding information of this building. There are dubious emergency exit signs, and it is not clear if the evacuee has to go to the terminal, to the baggage claim to finally reach the exit. So a modeler may assume that the evacuee will easily find his evacuation path, but this condition, as you can see, cannot be met in reality. Given all the problems that we have seen so far, do you think that people who go back into the building, if it were a model? Consider this example. This is Carattin in Venice. This is an exterior emergency exit stair that loops back into the building that may be on fire. Who expects to have to go back into the building to finally reach the exit? Without a person from the staff, people wouldn't probably understand that they have to go back into the building. Predicting behavior may not be always possible, but it can be controlled. In every stage of the fire response, dynamic control evacuation devices could be used to direct people in accordance with rapidly changing conditions of the built environment. But in order to do that, it is important that evacuation models are used as a tool to gain insights in order to clearly state all the uncertainties present in evacuation prediction. So engineers need to consult other professions on the difficulties and problems of predicting human behavior. Assumptions that behavior is reliable and predictable cannot be made without a far stronger research base. Assumptions used in models should be explicit to prevent misuse and mistakes, especially all the assumptions that relate to uncertainty. In conventional buildings, large margins of error, namely safety margins, are a possible response to uncertainty. In unusual buildings, model may have limited predictive ability. So our position is that when you have the uncertainties, you should design redundancy system to cope with the uncertainty. I'd like to end with this quote from Albert Einstein, just to make you remember that models are abstractions of reality. So it is important that they are used as a tool to gain insights about evacuation prediction and not only as a tool to get regulatory approval. But in order to do that, we have to work together with professionals that has a sort of heuristic knowledge able to clearly create a link between people and the built environment in order to foresee the evacuation modeling problems. And I thank you for your attention, and if you have any additional questions, I'm here to answer. Thank you.
Thank you. Thank you. We have time for a few questions.
It's very interesting, and it's not often you go from Isaac Newton to Albert Einstein in a evacuation modelling discussion. But 2 points. The example of the steps in the, I think is that at the University of Maryland? Those steps right at the beginning.
The first one with the crowd crush, yeah.
Is that a failure of the evacuation model or the process? Because, I mean, the way that model was set up was obviously incorrect. It should have pointed out that that was a problem, but surely the engineer and the person reviewing the material should have noticed that this was just a very bad idea. I mean, so is it as much a failure of the whole process as it is of the individual model being employed? And secondly, and so it's a valid point, though. I mean, that should never have been got through. But secondly, the issue of the changing use of a space over time is obviously incredibly important, and that the analysis of human performance isn't a one-off task. It can evolve. But isn't that just as much a problem for prescriptive codes as it is for performance-based codes, because the way that a building is used may change slightly over time, like with the artwork on the stairs. So I agree that that's a problem with the model, as long as the model can be an egress, a computational tool or an engineering tool or a prescriptive tool. So there's the same limitations, for sure. It has to be, the timeline issue is an issue for all approaches to design, really, as much as the models we're talking about as well.
Yeah, that's a good point, because it states that we not only need a validation protocol for evacuation model, but also for the users who have to select the proper input data. For example, here, it is a failure of the whole process, because the evacuation modeler forget about the crowd, but it complied with the codes. So it's only a problem of prescriptive code, because prescriptive code said that the handrails had to be parallel. So it's a mixture of code compliance and evacuation model. So it's not only a matter of focusing on evacuation model, but on the whole design process and how these are used. And can you repeat the second question? Okay, yeah.
The second question was just about it's a similar point.
Oh, okay.
That the use of a building over time may change, and that's independent almost of the origin of the original analysis. The problem there is that the use of the space needs to be specified very clearly and checked. It's a maintenance issue as much as anything else.
Yeah, it should be regulated. There are some building characteristics that should be regulated. Otherwise, that you fall into uncertainty, and you have to be clearly aware of the uncertainties.
Okay. Well, thank you very much.
Maybe that's Enrico.
Oh, Enrico.
Yeah, one thing about the, let's say, user protocol. An expert user doesn't mean necessarily a good user, because an evil expert user is the worst. If I know how to use a model that is let's say, a black box, I can get the results that I want. And an inexpert regulator or an expert authority in a jurisdiction will not figure out what I'm doing. So probably the stress should not be only on the users or on the developers, because I know it's a lot of pressure for the developers as well to provide good validation. But we should also redirect a bit the responsibility to who is approving the buildings. So that's the point. Like, I don't see having let's say, a validation protocol, like a license for users as the solution, because I repeat, I can get the results that I want if I really want to tweak the model. And the problem is an ethical issue then becomes, not just the negligence is not the only issue. That's what I want to point out.
It's an ethical issue. You have to be aware that you have to link the people and the built environment, that you are not only using a model, but that model is a tool that serves to predict human behavior in the event of an emergency. It's not something in itself. It's something that you use for a specific scope, and that specific scope is to design the built environment, a safe built environment.